Hundreds of billions of stars in our galaxy alone. Hundreds of billions of galaxies in the observable universe. Trillions upon trillions of planets, many of them sitting in the habitable zones of stable stars, bathed in the right amount of light, built from the right materials. The numbers are so staggeringly large that the conclusion seems inescapable. Life must exist out there. Intelligent life. Civilizations. Somebody, somewhere, looking up at their own sky and wondering the same thing we wonder. And yet we've found nothing. 60 years of searching radio, telescopes scanning the sky, optical surveys sweeping across millions of stars, spacecraft visiting every planet in our solar system. Thousands of exoplanets catalogued, their atmospheres analyzed, their compositions measured, and after all of that, silence. Complete, total, unbroken silence. This is the Fermi paradox, and it remains the single most disturbing, unanswered question in science. If intelligent life is common, where is everybody? Today we're going to explore an answer that most people haven't considered. An answer that doesn't involve galactic empires hiding from each other or civilizations destroying themselves in nuclear wars. An answer that's far simpler and in many ways far more unsettling. What if every civilization becomes invisible? Not because it dies, but because it grows up. Think about Earth right now. We've been broadcasting radio signals into space for roughly a century. TV, radio, radar, satellite communications, all of it leaking electromagnetic radiation outward in an expanding sphere. Right now, our signals have reached approximately the nearest few thousand stars. Anyone listening within that radius could, in theory, detect that something interesting is happening on the third planet from our sun. But here's what most people don't realize. That sphere of detectability is already shrinking. Not because we're broadcasting less, because we're broadcasting smarter. We're switching from omnidirectional radio towers that spray signals in every direction, including straight up into space, to cellular networks, fiber optic cables, and tightly focused satellite beams. Our communications are becoming more efficient, more directed, less wasteful. Every watt of energy that radiates uselessly into space is money thrown away. It's heat dumped into the void for no purpose. And as any civilization's technology matures, the economic pressure to stop wasting energy becomes overwhelming. You don't stop communicating. You stop communicating in ways that are visible from light years away. Think about it from an energy perspective. We fly over cities at night and see billions of watts of light blazing upward. Streetlights illuminating the sky, greenhouse facilities beaming light into space, buildings glowing like beacons. None of that light serves any purpose once it leaves the atmosphere. It's pure waste, and we're already working to eliminate it. Not because we're trying to hide from aliens, but because we're trying to save money. The same principle applies to radio. The age of powerful omnidirectional broadcasting is ending. We're transitioning to systems that keep their signals close to the ground, pointed at specific receivers, carried through cables rather than through the air. Each generation of communication technology is harder to detect from space than the last. This means that the window during which a technological civilization is electromagnetically visible might be shockingly brief. Maybe 100 years, maybe 200. From the moment a civilization discovers radio to the moment it stops leaking detectable signals into space. That's the window, and after that it goes dark, not dead, just efficient. Now multiply that across the galaxy. If the average civilization is detectable for only a century or two out of a lifespan that could stretch for millions or billions of years, the odds of two civilizations being in their loud phase at the same time and close enough to hear each other become vanishingly small. We might be surrounded by ancient, thriving civilizations that we will never detect because they solved the energy problem long ago and stopped shouting into the void. But there's another possibility that's even more unsettling. What if we're not surrounded by ancient civilizations? What if we're the first? This is the part where most people's intuition rebels. The universe is 13.8 billion years old. Our sun is only 4.6 billion years old. There were billions of years of cosmic history before Earth even formed. Surely someone else got there first. But surely is not a scientific argument, it's a feeling, and feelings can be wrong. The Drake equation was created in 1961 by astronomer Frank Drake as a framework for estimating the number of detectable civilizations in our galaxy. It breaks the problem into a chain of probabilities. How many stars are suitable? How many have planets? How many of those planets are habitable? On how many does life actually arise? On how many does intelligence evolve? How many develop technology? And how long do they remain detectable? We can now estimate most of those factors with reasonable confidence. Suitable stars, hundreds of billions; planets in habitable zones, millions at minimum. The raw materials for life are everywhere, we've confirmed that. The universe is practically drowning in the building blocks. But there's one factor in the Drake equation that nobody can estimate, and it's the one that matters most. What is the probability that life actually arises on a habitable planet? We have exactly one data point, Earth. Life appeared here, but we have no idea how likely that was. It could be nearly inevitable, a natural consequence of the right chemistry persisting for long enough, or it could be fantastically improbable, the result of a specific sequence of extraordinarily rare events that just happened to occur here and essentially nowhere else. The common argument goes like this: with hundreds of billions of galaxies, each containing hundreds of billions of stars, it can't be that life only arose once. But this argument is mathematically hollow. If the probability of life arising on any given habitable planet is sufficiently small, say 1 in 10 to the 30th power, then you can multiply it by every planet in the observable universe and still get a number less than 1. A very small probability multiplied by a very large number of chances can still produce a very small result. We simply don't know where that probability falls. It could be high, it could be unimaginably low. And until we find a second independent origin of life, on Mars, on Europa, on Enceladus, anywhere, we cannot distinguish between these two possibilities. This is why the search for microbial life on Mars matters so much more than most people realize. It's not about finding bacteria, it's about answering the most fundamental question in biology: is life a cosmic inevitability or a cosmic accident? The experiment neither confirmed nor denied life on Mars, and we haven't repeated it since. But here's the crucial point: even if life once existed on Mars, it almost certainly wouldn't survive on the surface today. The surface is bombarded by ultraviolet radiation, the atmosphere is thin, temperatures are extreme, and the soil chemistry is hostile to organic molecules. If Martian life exists, it retreated underground billions of years ago, following the water as it sank into the subsurface. And there's indirect evidence that liquid water still exists on Mars at depths of roughly 1.5 kilometers. Down there, geothermal heat keeps temperatures above freezing. The pressure is sufficient for liquid water, and we know from Earth that microbial life thrives in similar deep subsurface environments. Extremophiles, organisms adapted to extreme conditions, have been found kilometers below Earth's surface, living in cracks in rock, feeding on chemical energy from mineral reactions, completely independent of sunlight. If something similar exists on Mars, it's 1.5 kilometers down, and we can barely drill a few centimeters with our current robotic missions. The Kola Superdeep borehole, the deepest hole ever drilled on Earth, reached 12 kilometers. And that was a massive engineering project on our own planet, with unlimited access to power, materials, and human technicians. Drilling 1.5 kilometers on Mars with a robot from 225 million kilometers away is a challenge that probably won't be met until human crews are present on the surface, which means the question of Martian life may remain open for decades. But imagine for a moment that we do find it. Imagine that a future Mars expedition, robotic or crude, drills deep enough and discovers unambiguous microbial life in a subsurface aquifer. What would that mean? Everything. If life arose independently on Mars, truly independently, not contamination from Earth or transfer of organisms between planets via meteorite impacts, it would mean that the origin of life is not a freak accident. If it happened twice in one solar system, it must happen routinely across the universe. the probability factor in the Drake equation would shift from unknown to high, and the implication would be inescapable. Life is everywhere. But what about contamination? This is a genuine concern. Earth and Mars have been exchanging material for billions of years. When large impacts hit either planet, they blast rocks into space, and some of those rocks eventually land on the other world. We've found Martian meteorites on Earth. Theoretically, Earth rocks have landed on Mars too, though the dynamics make Earth to Mars transfer less efficient than Mars to Earth. And then there are our own spacecraft. The early landers weren't sterilized, later ones were. But no sterilization is perfect. There's always a risk that Earth microbes hitched a ride and contaminated the landing site. Distinguishing native Martian life from Earth contamination would require careful biochemical analysis, different enough molecular structures, different enough genetic mechanisms to prove independent origin. This is why the question of whether we're alone remains genuinely open, not leaning one way or the other, not probably yes or probably no, genuinely completely open. We lack the single piece of information that would resolve it, a second example of life arising from scratch. And this uncertainty carries a weight that goes beyond scientific curiosity. If we are alone, truly cosmically alone, then our civilization carries a burden unlike anything we normally contemplate. We are not just one species on one planet, we are the universe's only experiment in consciousness, the only place where matter has organized itself into something that can observe, question, and understand. If we destroy ourselves through war, environmental collapse, or simple neglect, it's not just a human tragedy, it's a cosmic one. The universe tried once in 13.8 billion years to produce something that could comprehend itself, and it failed. The Soviet astrophysicist Iosif Shklovsky put it memorably: "We are the vanguard of matter in the universe, the leading edge of complexity. And if we're the only vanguard, we can't afford to fall." But there's an even more concrete version of this existential pressure, and it has nothing to do with asteroids or nuclear war or climate change. It's the sun. Our sun is getting hotter. Not quickly, not in any way that matters on human timescales, but steadily and inevitably. The sun's luminosity has increased by roughly 30% since the Earth formed, and it will continue increasing as hydrogen fusion gradually changes the composition of the core. In approximately 1 to 1.5 billion years, the sun will be luminous enough that Earth's surface temperature will rise beyond the point where liquid water can exist. The oceans will evaporate. The atmosphere will undergo a runaway greenhouse effect. Earth will become uninhabitable. This is not a probability. It's not a risk that might or might not materialize. It will happen with absolute certainty. The physics is settled. The timeline is set. Or maybe the silence will continue. Maybe we'll keep checking rooms and finding them empty. And we'll have to learn to live with the possibility that the apartment is ours alone. All of it, every galaxy, every star, every planet, every moon, an infinite expanse of matter and energy, and only one tiny speck where anyone is home. If that's the case, then everything we do matters more than we ever imagined. Every war is a risk to the only consciousness in existence. Every environmental catastrophe threatens the only biosphere that has ever produced a mind capable of wondering whether it's alone. Every rocket that launches toward another world is not just exploration, it's insurance against extinction. We don't know if we're alone. We may not know for centuries, but the uncertainty itself is information. It tells us that we cannot afford to be careless with what we have, because if we're the universe's only chance at self-awareness, we don't get a second try. The cosmos is patient. It waited 13.8 billion years to produce us. But it may not be willing to wait again.